Hi and hello once again. So we are on our next problem here, which is more on capacitance problem. So we are on problem number 9. So let us read the problem first. So this is a former board exam problem, by the way. Okay, the shunt capacitance of a 120 kilometer 60 Hz, 34.5 kilovolt, 3-phase transmission line is 1,800 ohms per phase. What is the shunt capacitance of the line in a microfarad per kilometer per phase basis and the charging current as well? Okay, this is the solution. And please take note, we can recall some things from our discussion on capacitance, but in terms of units. So the Cn required must be microfarad per kilometer per phase basis. And recall the equation for XCn, which is 1 all over 2 pi FCn. And please take note, by the way, the unit is ohm in a unit length. Simply because the Cn here, if you can still recall, for example, this is in farad per meter, if you can still recall that, per phase. The meter here will go here, right, on the numerator part, and 1 over 2 pi fc, which is in farad, the answer is ohm. So thus we can say that is ohm dash length. Now this is different, guys, for XL, since you have 2 pi fl and your L here is Henry per meter. Okay, so thus the meter here is a unit length, and your XL, the unit is ohm per unit length. Always the inverse, okay, on these two terms of capacitance and inductance. So your XCn must be ohm per unit length. So in this case, ohm per meter. Okay, let us move forward now. So just rearrange the equation. So you have your Cn 1 over 2 pi f, which is 377 or 2 pi 60, 1,800 is the XCn, and then 120 kilometer. It must be ohm dash kilometer. And thus, we have here in farad per kilometer basis, so that is 0.012228 times 10 to the negative 6, or in microfarad per kilometer per phase. Okay, a very, very simple problem, guys. Now, if you want to get your IC magnitude, okay, all you have to do is to have this equation is already pre-given even on our your power factor correction. Okay, power factor correction. So you have IC is omega Cn VCn, right? So in this case, your C now is this value here. Your omega is 377 for 60 Hertz, and then your VCn is a 34.5 in a line-to-line basis. You divide it by square root of 3. Manipulating it and having it in your calculator, the answer is 11.06 ampere per phase basis. So very, very simple problem here. All you have to do is to recall your basic formulas and concepts. Let us move forward to number 10. Hi and hello once again. Let us solve the last number on the parameters of the line under the capacitance, which is problem number 10. Okay, so let us have the problem. A 115 60 Hz 100 kilometer line 3-phase transmission has a horizontal configuration with a distance of 3 meters between adjacent phases. So the radius of each conductor is 0.915 centimeter. We need to find the shunt capacitance in microfarad per kilometer per phase basis, as well as the capacitive reactance in ohms per phase. So the solution is straightforward, since we already discussed this in the last few slides, that Cn is equal to 2 pi EO ER all over ln D equal over R. However, the relative permeability or permittivity rather of air or aluminum rather is 1 for an aluminum or copper. So automatically, this one is equal to 1. Unless if your conductor is another type or another material. So 2 pi EO all over ln DEQ all over R, which is in terms of farad per meter per phase. And this is a 3-phase, 3-wire horizontal configuration. So for this, you have 3 conductors. We have A, B, and C, which is 3 meters apart. So for this, okay, we have DEQ is equal to cube root of DAB, DBC, and DCA. So please take note, okay, that this formula is already given to you from the last few slides. So DEQ is equal to cube root of 3 squared times 6. We have 3.78 meters or 378 centimeters if we multiply it by 100. So thus, by substitution on this formula, we have 2 pi 8.85, no, which is E, that is your EO constant, times 10 negative 12 times 1, ln 378 all over 0.915. Both the centimeters here will cancel out. In 1 microfarad, you have 1 times 10 negative 6, and then you have 1,000 meters in 1 kilometer. So it will cancel all the parameters here, leaving behind microfarad per kilometer. The answer is Cn is equal to 0.0923 microfarad per kilometer per phase basis. So this is the capacitance. Now, if you want to get the reactive capacitance, or rather the capacitive reactance, rather, you have Xc all over 1 2 pi f Cn. But 2 pi f here will depend on frequency. So if your frequency is 60 Hertz, you have 377 radian per second. And thus, by substitution, 1 all over 377 times 0.0923 microfarad, no? Microfarad. And you need to multiply it by 100 because the answer here is per kilometer and we need the answer in ohms only. Thus, Xc is 2.874 ohms per phase. So, we can now proceed to the next problem. Stay tuned. Hi, and good day to all of you. So, we are in our last problem for the topic of parameters of the line. So, let us read the last problem in capacitance. The conductors in a single phase 10 kilometer transmission line are 6 meters above the ground. So it has now has an effect of the height. Each conductor is 1.5 centimeter in diameter and the conductors are spaced 3 meters apart. If the supply voltage is 33 kV, determine the following: the capacitance of the line, no, with the effect of the ground. Letter B, the capacitance of the line, neglecting the effect of the ground. So let us see if there's any difference. And the charging current. Okay, without further ado, let us have the scenario here. You have a single phase 2-wire line. You have the height. You have the distance between conductors. You have the diameter, D. So by dividing it by 2, you have a 0.75 centimeter radius. The voltage is 33 kV in a single phase 2-wire line. So we must recall the equation here. Say AB plus the effect of the height is pi EO all over ln D all over R, and this is the effect of the height equation, which is square root of 1 plus D squared over 4H squared. So this is in farad per meter between conductors. So we need to simplify things up. So here you have 0.75 for the R, 1 plus D. This is the distance between conductors. By the way, the D here is also the D at the numerator part. So 300 squared all over 4, all over 600 is squared, which is the height is 6 meters. The answer is 0.77308 centimeters. Now, by substitution, no, it has an ER here, by the way, but here ER is equal to 1, which is the permittivity of aluminum or conductor. So we already disregard the ER here, which is simply equal to 1. So you have 8.85 times 10 negative 12, no, farad per meter, and then you have 1 microfarad, 1 times 10 negative 6 farad, and then 1,000 meter, 1 kilometer, so that we can cancel meters, and then the farad to become microfarad only, but we need to multiply it by the length, which is 10 kilometer. So the answer here is CAB plus the height is 0.04664 microfarads. And if we do this also with without the effect of the height, the parameter here will be equal to 1. So it will become d all over r only. So if we do so by substitution all of the variables here without this term, we will have here 0.0464 microfarad. So there's a little bit of discrepancy or increase, okay, in the capacitance with the height. And the charging current is V phase all over XC. If we rearrange the equations here, it will become 2 pi FC V phase. However, the omega here is automatic 2 pi F, which is 377 radian per second for a frequency of 60. By substitution, you have 33K, 377, and then this one, we use the CAB only and without the height effect, or 0.0464 times 10 negative 6. Thus, the answer is 0.5772 amperes. So, that concludes the parameters of the line RLC. So, our next topic is a very interesting topic, which is under the transmission and distribution subject, which is the performance of the line. So, maraming salamat po sa lahat, all of the subscribers who listens, who already be patient on my discussions. So, thank you, and God bless, and stay safe. Ciao, kapatid.